So what I'm going to try and do then is, so Simon brought you up to really the current cutting edge, state-of-the-art in research. My approach has been different. I'm trying to be pedagogical. And so I'm going to carry on that vein and try to show you lots of movies in order for your phase space in your brain to reconfigure itself. And so here's where I stopped last time, 2 days ago. I talked about linear theory and how we can calculate mathematically the evolution of perturbations in the early universe under the assumption that the initial conditions were quantum fluctuations generated by inflation, and that the universe contains dark matter, which then changes the initial Harrison-Seldovich n=1 spectrum, as shown here in the case of cold dark matter. And so I spent then that lecture telling you about the evolution of perturbations in the first few 100,000 years of the universe, when perturbations are still small. And then the question is, how do we go from that linear theory power spectrum to be able to account for the structure that we see in the universe today? And although the physics here is very simple, and indeed all the physics in Simon's talk was purely gravity, in spite of the complexity, it was all really gravity. The calculations are complex because the systems that we're interested in are strongly nonlinear and non-spherical, and that's why we need embodied simulations. So I started telling you a little bit about embodied simulations. I pointed out that luckily we don't need general relativity in cosmology for these kind of calculations, and the way in which what really is an attempt to solve the Blasov equation is implemented in practice is by discretizing the system into particles, which should be viewed as a Monte Carlo realization of that continuum field. And so the problem reduces to solving 3n, where n is the number of particles, couple second-order nonlinear differential equations. And that is the embodied problem. So what I'm going to do now is I'm going to tell you how Simon carries out the simulations that you just heard about. So when you do an embodied simulation, the first thing you realize, because in cold dark matter the structure is hierarchical, that there are two conflicting demands upon the calculation. On the one hand, you want to have a small particle mass in order to resolve all these subhalos and so on. On the other hand, you want to simulate a large volume because you want to have many examples of the objects that you're interested in. And these two pull in different directions. Small mass requires you, if you want to resolve objects, means that because the computer resources are finite, that you can only do a small volume, and that directly conflicts with the need to have a large volume. So the way in which these two conflicting demands are resolved is by increasing the number of particles in the simulation. And if you don't do that, you run into lots of problems. For example, if you have a volume that's too small, as I just said, you don't find enough objects. There, for example, no rare objects, no first halo, rich clusters, and so on. And something even worse happens is the computational volume is too small. Then it comes a point where the whole box wants to collapse. We refer to that as saying that the fundamental mode goes nonlinear, and the calculation is no longer valid. On the other hand, if you don't have enough particles of sufficiently small mass, then you cannot resolve all the exciting stuff that Simon was telling you about. So how do you do that? Well, I'm going to tell you about it in a minute. But you can see here that these conflicting demands have led to an extremely rapid growth in the size of simulations from the 1970s, where Jim Peebles carried out the very first embodied simulation in cosmology, to the Millennium simulation that some people have already talked about before. And here, this plot shows the number of particles in a simulation as a function of year, from 1970 to about 2004. Now, as we know from Moore's law, computers double in speed every 18 months. And yet, this is actually faster than Moore's law. The simulations have doubled their size every 16.5 months. And I'll tell you why in a minute. For example, the Millennium simulation, which had 10 to the 10 particles, should have, even according to this line, not have been possible for 4 years after it was actually possible. And I'm going to tell you why simulations have increased faster than you would expect just from the increase in computing power. Now, maybe I'll highlight some important calculations here. These were in the 1980s, the simulations that established the CDM cosmology as a viable cosmology. I'm going to tell you a little bit more about those. And then along here, simulations of individual halos began to be made in detail. The Aquarius program that Simon was talking about before is actually low in particles. You really see here that tension, it's only 10 to the 9 particles, so it more or less scattered around the line, but there you saw the requirement to have a small particle mass conflicting with the requirement of having this large volume, and that's why Simon could only talk about 6 halos, not about many large samples. So that's also illustrated here. It's a picture that says clearly the hierarchical nature of cold dark matter universe. Here we have the volume seen on very large scales. It's quite uniform. But as we zoom successively into smaller and smaller regions, you see how the universe, the cold dark matter universe at least, has structure on all scales. And that is what underlies this complexity. So Eric wanted me to tell you about how embodied simulations are carried out. And I'm glad to tell you that. And the main idea then that has allowed this rapid increase in particle number is illustrated here. Suppose you want to calculate the force on this particle. If you went around calculating the forces from every other particle on it, you'll have an n-squared calculation that would very soon burn up all your computing time. However, if you're sitting here, well, you really want to calculate quite accurately the forces from all these other particles that are nearby. But if you look at this lump here, well, the force from this particle and that particle on that one are very similar. So you don't really need to bother calculating each of them individually. You can lump them all together into one massive body, and then you can, for example, expand the potential field in terms of do a multiple expansion, which is very quick to do, and then calculate the force, not of each individual particle on that one, but of the whole collection. And that is the basis of the code that carry out the simulations Simon told you about. The way you do that in practice is by constructing a tree. For example, in this two-dimensional example, you divide the volume into 4 parts recursively. Each part then gets divided into 4. And in this way, you build up a hierarchical tree which allows you to implement this idea very efficiently. When you do that, then instead of the calculation scaling like n squared, scales only like log n.
But how much does the calculations differ from the more accurate case where you take into account each particle?
If you do it correctly and adjust parameters correctly, then you can control the accuracy almost arbitrarily, to arbitrarily good accuracy. And, for example, Simon showed you these convergence studies that are a manifestation of the accuracy of the integration. So you can do that very accurately.
Sorry, what tree do you use to separate between the particles?
What?
That tree that you made.
Yeah, it's just a hierarchical. What actual implementation is used, it is just a tree. It's just a hierarchical tree. Okay, so then now, however, that's called a tree code. Now, tree codes are much faster than n squared, but they're still not fast enough for the problem in hand. And the other complementary technique that's used was implemented for the first time by Volker Springel in his code Gadget 2, which is publicly available. Although this is not the code that Simon used. Simon used Gadget 3, but the principles are the same. And the idea here is to recognize, first of all, that, of course, we're just solving the Poisson equation here. And the Poisson equation in real space is a complicated second-order differential equation. But in Fourier space, it becomes very simple to solve. It's just an algebraic equation. So if you go to Fourier space, the Poisson equation is just a simple algebraic equation. And it turns out that doing Fourier transforms is something that computers are very good at. They can do that very fast. So what you do then is you have a density field, and you bin it in a mesh, and then you can do a Fourier transform very efficiently in a computer. Of course, the minute you do that, you've introduced a mesh, and that introduces a resolution limit, which is the mesh size. So the great breakthrough was to combine this idea with a tree code, such that on large scales, one computes the gravitational field, the gravitational force using the Fourier technique, and on small scales, inside each cell, if you like, then you use a tree to refine the calculation and make it accurate. So that's what Gadget 2 does. It combines a so-called particle mesh method based on fast Fourier transforms to compute the long-range gravitational force, and then it computes a short-range gravitational force using a tree algorithm like I just described. And here is the force as a function of radius. If you look at this, you say, well, wait a minute, that's not how gravity works. As I go to 0 radius, the force should diverge. In simulations, we have to introduce a smoothing in order to prevent singularities when two particles get very close together. That's called the softening length. And so the forces are softened towards the center as the distance between particles becomes small. Now, so we've been talking about embodied simulations only involving gravity, but of course the real universe has galaxies and has stars and gas and so on. And so if we really want to make contact with the real universe, we need to be able also to simulate the evolution of gas. And that is a much more complex problem. Here are the equations that one needs to solve. Is the Euler equation. Here, the mass conservation continuity equation, the first law of thermodynamics, and the equation of ideal gas. So these are the 4 equations that one needs to solve just to follow the gas. In addition to that, you need to have a method for finding out how the gas would eventually turn into stars, and how the evolution of stars, in fact, affects or feeds back into the evolution of gas. But these are the basic hydro equations on top of which you need to put in a model of galaxy formation. So there are 2 approaches to solving the hydro equations: a Eulerian and a Lagrangian approach. And in the subject, most work is done using a Lagrangian technique, which, for example, is implemented in the Gadget code. And as I say, Gadget is actually publicly available, and anybody who wants to get initiated into doing simulations, you can just download it from the web, and it's all pretty self-contained. Please do not email Volker Springel unless you really have to. All right, so nobody should email Volker until they've exhausted every other possible source of solution to the problems. Now, so in the Eulerian approach, is based on discretizing space in a mesh. The mesh might actually be an interesting mesh that can adapt its resolution to the problem, but it's essentially a mesh. And you solve the hydro equations by a finite difference approach, computing fluxes of mass, energy, and so on from one cell to another, and advancing the system that way. And the principal advantage is that you can solve by finite differences. You can solve differential equations very accurately. You can capture shocks, resolve shocks with high accuracy, and there's low numerical viscosity generally in good quality codes of this sort. The problem, of course, is you have a mesh, and that limits the resolution. And even with the higher generation of codes called adaptive mesh codes that refine the mesh whenever something interesting happens, you're still limited in resolution by the nature of the approach. The alternative is to use a Lagrangian approach where you don't discretize space, you discretize the mass, and then the fluid is represented by particles, just like we did with the embodied case. This is inspired really by embodied simulations. And what you do here is that you smooth over the particle. You average, if you want to know the density at a point, you take an average, suitably weighted average of the densities carried by particles around the point you're interested in, or around a particle you're interested in. And likewise, you obtain smoother averages of all the important thermodynamic quantities: density, temperature, pressure, internal energy, and so on. And so the calculation then moves with the fluid, and the great advantage of this approach is that the resolution naturally adjusts to the problem. So you have equal resolution if the particles are distributed in a big configuration, as you do when they collapse, because you're following the flow as you go along, unlike in the case of a Eulerian calculation. So the downside of this so-called smooth particle hydrodynamics approach is, of course, that you cannot solve the equations with the same accuracy as you can in the Eulerian case. So, for example, shocks are not very thin. They're actually spread out just because, as the name indicates, you smooth over properties. Shock is something that's sharp, not smooth. And so that is the main limitation of the Lagrangian approach. Now, so I could spend the rest of the morning telling you about this. I decided to go back to science. Those are the basic ideas of techniques. Anybody wants to know more about them, I'll be happy to give you references where you can learn about it. I would say you could start with Volker Springel's public release of Gadget. Now, so let's go back to what we want these codes for. What we want to do then is to simulate the nonlinear part of evolution of a universe dominated by different kinds of dark matter, for example, hot or cold dark matter. Now, that program then began in the 1980s, and if you recall, as I said yesterday, there are really two extremes within this kind of general philosophy or general set of theories. Two extremes, cold dark matter being one, where the scale on all, structure on all scales, on scales of superclusters, clusters of galaxies, and even below that. And that's what Simon has been talking about. But there's the other possibility that the dark matter might be hot. For example, a neutrino with a mass of a few tenths of electron volts, in which case this free streaming that I talked about last time would wipe out all structure on small scales such that superclusters would form first, and galaxies and galaxy clusters then would form by fragmentation from these big pancakes that would form first. And so in the 1980s, people began to simulate the nonlinear part of evolution of, for example, a neutrino-dominated hot dark matter universe. And you see here the results of these are very old simulations. They had, unlike, say, the Millennium simulation, which has 10 billion particles, these had 32,768 particles. I even remember the number because I knew what each of them was doing. And you see here what a universe dominated by hot dark matter would look like. These are two choices for when one thinks galaxies formed in these two models. That's what it would look like. That's a patch of universe of size about 100 megaparsecs in a hot dark matter universe would look like that. Now, how do we know if this was realistic or not? Well, in the 1980s, the first gigantic galaxy survey was carried out that was called the CFA Redshift Survey, with a grand total of 2,543 galaxies. This survey was carried out by John Hookra, Mark Davis, and Margaret Geller. And you can see here what the survey looked like as seen on the sky, and here in one of these characteristic often used pi diagrams where you plot velocity in this direction and recording it on the sky. Now, so that was 1982. In 25 years, we'd gone from this to 2DF and Sloan. Now, however, if you compare the advance in the number of galaxy redshifts measured from 2000 to the 500,000 in Sloan, you can see that theories have made a lot more progress than observers because the number of particles in simulations has increased by many orders of magnitude more than the number of galaxies in redshift surveys. Nevertheless, laughable as these surveys look like, they were good enough to rule out a universe dominated by hot dark matter. And so you see here this often used phrase nowadays, size is not always important. And you can see here that these neutrino-dominated universes didn't look at all like the CFA Galaxy Redshift Survey. These great big structures that formed in these universes did not have any parallels in the observed CFA Redshift Survey. So we were able to argue that the universe could not be dominated by hot dark matter. And moreover, that implies, of course, that the neutrino mass cannot be large. Neutrinos could not make an appreciable contribution to omega. And so we concluded here that the neutrino mass, if it existed at all, had to be much less than 10 electron volts. And 25 years later, we know that that conclusion from cosmology is actually correct. So this is one example of how you can use cosmology to learn about particle physics. That was the first time a limit was set on the neutrino mass from cosmological considerations. Very good, so hot dark matter didn't work. Then you immediately then tempted to consider the possibility of cold dark matter. And that's what we did in the 1980s. And here you see again the CFA survey. This is a picture from the previous slide of neutrinos. And here's the cold dark matter universe. Now this cold dark matter universe clearly looks a lot more like the CFA, a lot more, certainly much better than the neutrinos. Unfortunately, when we carried out the simulation, we found something really, really annoying. You needed omega of 0.2 in order to have a good match to the data. Omega 0.2 in 1982 was like saying George Bush is the most intelligent man on earth. People would laugh at you. They would isolate you at dinner. Nobody wanted to sit with you. And omega 0.2 was just not on. Huh? All right. So omega 0.2 was just not on. So we put in a cosmological constant, what people call Lambda CDM, and the plot looked just the same. It looked pretty good. Now, if you thought an open universe was bad, the cosmological constant in 1982 was sinful. It was calumny. You could be burned on the stake for talking about a cosmological constant in 1982. So we didn't like this, and we thought, why? Let me say, an open universe was no good because we're starting from inflation, and inflation predicts a flat universe. So that's why an open universe was no good. And the cosmological constant, people would really be very rude about you. They would say the cosmological constant is the last refuge of the, of what, Simon? The last refuge of the perverse, the malevolent. So,
when you say Luke,
well, I'm going to show you some statistics in a minute. Right, so omega equals 1 was what one needed, but omega equals 1, CDM had two problems. Firstly, it turns out that the clustering was wrong, but also, if you have a universe with omega equals 1, there's a lot of gravity, and so gravity pulls, and the particles were moving much too fast compared to observations of velocities of galaxies. So this omega equals 1 model had two problems, the wrong clustering and too large peculiar velocities. However, the ingenuity of theorists is unlimited, and it was soon recognized that you could solve this problem by assuming that the galaxies do not follow the same distribution of mass, but instead that galaxies form only on peaks of the density field. That was an idea that Nick Kaiser had introduced in order to explain why galaxy clusters are more strongly clustered than galaxies, and that idea was then transported to galaxies. And if you argue that galaxies don't form wherever there is dark matter, that statistically the galaxies don't just trace the dark matter, but form only in the high peaks of the density field, then it's known from communication theory that high peaks of a density field are more strongly clustered than the underlying field. And so you could then get away with a model in which the dark matter was much smoother than the galaxies, and therefore, because it's much smoother, the velocities would be smaller, and solving the problem of peculiar velocities. So, moreover, you could actually get even the right galaxy clustering for this biased galaxy formation picture. And the bias here was quite strong. Galaxies where the density field of galaxies was about twice or 3 times more strongly clustered than the underlying dark matter. So this gave rise to the idea of biased galaxy formation, which survived for about a decade and gave rise to some very excellent papers, like a paper by Bardeen, Bond, Kaiser, and Saleh that everybody really ought to read in their spare time, if they have any. Simon once said that this idea set the subject back 10 years. I don't quite agree with him. It was a lot of fun trying to make omega equals 1 work. And it did work for quite a number of years in the 80s, because in the 80s, really, observations were still at a very rudimentary stage, and so you could get away with lots of things. As a theorist, there weren't really observations of sufficient quality to compare these, to rule out these sort of ideas. Here's an example. Here's the CFA survey that I showed before. This used to be called the Harvard-Stickman, and these are two bias, omega equals 1 bias galaxy formation simulations that you can see capture this essentially the nature of these distributions. And in response to Omar, I don't have plots here. If you calculate the correlation function or the power spectrum, they were perfectly acceptable given the limited amount of data that existed at the time. Now, things started going pear-shaped around 1990. This is a very important plot in the development of cosmology that is often unappreciated. This was work by George Eustathiou and collaborators, and they had a very large galaxy survey of 1 million galaxies, which they scanned with a machine. This was just projected on the sky. They had no redshifts, but they had a very large number of galaxies, and they were able to compute the projected 2-point correlation function as a function of angle on the sky. And what they recognized was that the CDM model, this biased galaxy formation model, although it agreed quite well with the data on small angular scales, on large scales that were being probed for the first time, 50 megaparsecs, this was the first time anybody could talk about clustering on these large scales. The data had more power than the predicted by the standard Koldak-Mare model. So the Koldak-Mare model fell short by a factor ranging from 2 or 3 at these sort of scales up to an order of magnitude or more. There just was not enough power in this bias field. The dark matter was very smooth because of these amplification in the bias for the galaxies, and so the clustering just did not have the right shape. Now, so what they concluded in a subsequent paper led by George Eustathiou was the solution to this problem was to go back to the model that we had issued earlier on and add a cosmological constant. So they wrote a very important paper in 1991 arguing that the solution to this problem and other problems of the standard Koldak-Mare model lay in the cosmological constant. And so it was already clear by 1990 the wind was beginning to blow in a different direction, and it was clear then that a cosmological constant might play a role. Now, a further development that I think was important in the 1990s was the realization that omega could not really be 1. And there was a very simple argument that I will try and explain in 2 minutes because it's so simple, but it is very powerful because it is so simple. And that is an argument that consists merely of doing an inventory of what galaxy clusters contain and comparing that with what you expect from the spherical top hat collapse model that I talked about on Tuesday and that Simon also illustrated in his plots from Ed Bertschinger a little while ago. So you go to a galaxy cluster and you can very easily and very accurately figure out what a galaxy cluster contains. It contains gas, hot gas that emits X-rays. Here are some pictures of X-rays from clusters. And from the X-rays, you can figure out how much gas mass there is. But also, because the X-rays are in equilibrium, in hydrostatic equilibrium, or we think they're in hydrostatic equilibrium, you can also compute the total gravitating mass. So from gas, from X-rays, we know the gas mass and the gravitating mass. Just from counting stars, from photometry, you know how many stars there are. And you can check your gravitating mass calculation from lensing. And so we know how much baryons, how many baryons clusters contain and how much dark matter. And you can divide one by the other and work out this quantity called the baryon fraction. So that's just the fraction of the total mass in a galaxy cluster in the form of baryons. Now the beauty is that you can measure, as I just said, this baryon fraction. But theoretically, we know exactly what to expect because a galaxy cluster is an object that has followed the evolution shown here. It has expanded, reached a maximum size, collapsed, and typically the matter is just coming out the other side. So that in the case of a galaxy cluster, the edge of the cluster is around here. And so what that means is that everything that's fallen inside the cluster is still in the cluster. Nothing's come out of the cluster. Unlike in a galaxy, for example, where gas could have been expelled, in a galaxy cluster, everything that's fallen in is still there. It could have been rearranged, but everything that's fallen in is still in there. Now, why is that such a powerful idea? The reason then is quite simple. The baryon fraction in clusters is typical of the baryon fraction of the universe, because everything that's fallen in is still in there. Now we know we can compute the baryon fraction in clusters, but we also know how many baryons the universe contains, for example, from big black nucleosynthesis. So let me backtrack a second. So the baryon fraction, the statement here then is that the baryon fraction in a galaxy cluster is equal to the universal value modulus a small number of order unity, because things are not really spherical. And so the spherical collapse is just for illustration. This is a bias factor, if you like, that can be computed quite reliably from simulations using hydrodynamics. In fact, this number is almost 1. It's 0.9. And so we know the baryon fraction from observations. Big bang nucleosynthesis tells us the value of omega baryon, and you can solve this equation to figure out omega. And it was realized in the 1990s that with the data that was around then, and this is still true today, that omega matter could not be 1. It had to be less than 1. The error bars with this method are, of course, much larger than we have now from WMAP and so on, but this is a completely different argument. WMAP hadn't flown then anyway, but it is extremely powerful because it's so simple. So around the early 90s, it was clear that omega could not be 1, and it was also clear that to account for the clustering of galaxies and be consistent with inflation, there had to be a cosmological constant. So this is another example where the theories went one step ahead of the observers. This argument that I just given you would imply that big bang nucleosynthesis is wrong, which we know it's not. The universe had to be open, or the preferred solution, which was this one. It's an argument due primarily to Simon. So by the end of the 1990s, we had a panoply of cold dark matter models that were being used to compare with data. That some had omega equals 1, which we know from the argument I just given you are not be correct. This was what we used to call the standard cold dark matter model from the 1980s with biased galaxy formation. This was an attempt to, earlier attempt called tau CDM, to try still desperately to reconcile omega equals 1 with the data by saying that maybe the particles, the cold particles decayed, and that changed the power spectrum, thus accounting for the APM correlation function, but still these models had omega equals 1, which, as I've just shown, was not really viable unless big bang nucleosynthesis was wrong. And then there were these models, one without a cosmological constant, and this one, which we now know as Lambda CDM. Notice that from the point of view of large-scale structure, the cosmological constant does nothing. These two plots are very similar. Only if you look at the structure of the halos, there you begin to see differences because they form at different epochs. And as Simon showed, the formation epoch has to do with the concentration of the halos. So there are differences whether or not you have lambda, but they affect the structure of the halos, not the large-scale distribution. It's essentially identical. Therefore, when a few years later, Sul Perlmutter and his colleagues, and Adam Rees and Bob Kirshner and their colleagues published the supernova data indicating that there was a cosmological constant, the theories were perfectly au fait. We were quite agreeable to that because the need was clearly already there. Now, I should point out, though, that the original data is an interesting sociological comment. The initial supernova data didn't really tell you with any confidence that there had to be a cosmological constant. These data are usually displayed in a diagram like this, omega lambda versus omega matter. And if you ask, well, at what level of confidence can I rule omega lambda equals 0? You see this 1 sigma, that's 2 sigma. It's a little bit more complicated than this, but essentially you can see that omega lambda equals 0 in this early data was only, omega lambda not 0 was only, omega lambda equals 0 was only ruled out at less than 2 sigma. So the detection here of lambda was very marginal. Yet, the atmosphere was already such that people then embraced this idea. Okay, so we knew then that we better just zoom into this particular model. And of course, and so let me show you now, as I promised, as part of the decompression process from Simon's talk. I promised I was going to show some movies. So here is, I don't know if we can put the lights out for the movies. I guess not. So here's a movie that shows how structure forms in a Lambda CDM universe. This is an embodied simulation carried out with Gadget of a sphere, co-moving sphere, a sphere of co-moving radius 150 megaparsecs. And so you see it here very early on, about 60 million years after the Big Bang. The distribution is very smooth. And because these lights are... this is not so. This movie is not as spectacular as the ones that come next. So, great, thank you, Carlos. Right. So you see here the very smooth distribution. If you look very closely, you can see that it's not completely smooth. This has perturbations, as is appropriate in a cold dark matter universe. And you're going to see then the evolution of the sphere in co-moving coordinates. Otherwise, the screen would have to expand. And so in co-moving coordinates, we'll see how structure then forms from cold dark matter initial conditions.
You're using lambda.
Yes. I am it's Lambda CDM, yes. So, good, it works. Okay, so you have to pay attention. Structure forms very, very quickly. Remember, the growth rate tends to stifle at late times. And so you see how very quickly the universe goes in this Lambda CDM model from being very uniform to being extremely structured. So what happened was gravitational instability began to operate very soon at very early times, and material then fell into lumps, and you could see how these lumps had this sort of characteristic filamentary appearance that arises from nonlinear evolution of these Gaussian fields. Let me see if I can show it again.
Did you decide to stop the evolution at that time that you actually?
Well, the evolution, yes, the evolution runs for essentially until redshift 0. And so it starts at high redshift, and it goes on to redshift 0. So here, when the universe is only a few billion years old, it's already very strongly structured, and you see then the formation of this sort of characteristic filamentary appearance with matter concentrated in big lumps that are joined together by filaments. So this goes all the way to redshift 0. So it was evolved for 13 million years. Yep?
Sorry, in the plot before when you showed open CDM at point 2 and the Lambda CDM, why does Lambda CDM have more clustering? Because you add Lambda and why does that give more?
I was arguing they have the same clustering on large scales. The only difference are in the structure of halos, because they don't form at the same time. So halos of the same mass form at different epochs when the universe has different densities, just because the growth rates depend on the existence or not of lambda. So the fluctuation, the linear theory growth rate is fastest for a universe with omega equals 1, slowest for a universe with very low omega, no lambda, and intermediate for a universe with lambda. And so the growth rates are different, the formation epochs of objects is different, and therefore their internal structure is different, but the large scale clustering is insensitive to lambda. Okay, so, yep.
And towards the future, have you made any evolution?
Towards the future?
Yeah, and what happened?
Only by accident, right? Because all these calculations are very expensive. So, and they get more and more expensive as you approach the present, because they get more and more clustered. So you don't really want to go to the future. And we can talk about what happens in the future later. But let me now go back to how we test CDM. So the supernovae, yes?
About that.
Yes.
If we were not in the co-moving coordinates, if we were able to see the evolution, but the expansion,
No, there was
scale
no
factor. I mean, not in the co-moving coordinate,
Right.
but in order to see the expansion rate, will it be possible to see also some kind of acceleration in the late times?
In a movie, you mean?
Yes, in the
Well, no, not practical, right? Because, well, you could. Some people do movies where everything starts in a point.
I mean, it will be something
Sure,
like-
you can make a movie like that. We've made movies like that, yeah.
Will it be possible to see some expansion, accelerated expansion in late times? I mean, like the...
Well, you see it in the equations. The equations tell you yeah, you could do a movie.
The question, but in the simulation, in the way how you...
Well, these simulations have accelerated expansion. So because they have lambda, so the expansion has been accelerating since, redshift 0.8 or something. So they are like the real universe insofar as the expansion property. So one of the things you do in the simulations is you solve the Friedmann equation, and once you put in the values of lambda and omega and so on, then it does exactly what our universe does insofar as the expansion properties are concerned. So it's in there. The accelerated expansion is part of that. That's why the structure freezes. So when you look at the movie, the structure forms very early, and then it freezes out. Because as I was saying the other day, if you have a lambda term, then the growth of structure slows down as lambda dominates, and eventually it will completely freeze out in the limit of the Sitter universe, where there's just cosmological constant. There'll be no growth at all. So you see that that was present in there. That's why structure forms so quickly. Right, so wait. We,
To give time for questions.
all right, okay, but I thought I started at,
You started at 10:15.
at what?
10 minutes to 11.
Yeah,
10 minutes to
right, okay, all right. But my watch says 10:30.
Now you have been talking for
All right.
40 minutes.
All right, okay. So let me speed up then. So then the historical part was supposed to last 5 minutes. Anyway, so the supernovae came along, but really what clinched it was the microwave background. And this really was a completely unexpected result. To me, at least, who spent all my life working on CDM, I just couldn't believe this when it came out, because it just agrees so beautifully with the cold dark matter cosmology. And so, however, I think many of the young people have bought this too far, in my opinion, and stopped questioning the bases. The bases are that we have a model here that agrees beautifully with the data, but it assumes not only the dark energy, I think that's a very difficult, probably insoluble problem in my lifetime, but it does assume also the existence of cold dark matter. And that is something that we should be able to test experimentally. At any rate, so the microwave background then really established this as the paradigm, but we must realize two things. The microwave background probes the universe at redshift 1000 when fluctuations are of order 10 to the minus 5. Galaxies probe the universe at redshift 0 or 1 when the density contrasts are now 11 orders of magnitude or more bigger than they were in the CMB. Moreover, they probe different scales. The CMB probes large scales, whereas all astronomical objects of interest are on much smaller scales not probed by the CMB. So what's plotted here is the microwave background data linearly extrapolated to redshift 0, just using linear theory, as I discussed last time, extrapolate to redshift 0. And this is not shown as a function of CLs, but as a function of K, which you can do if you know what the geometry of the universe is. You can go from angular distances to true distances. And so this is a plot then of what these fluctuations would look like today if the universe had evolved linearly. And so the microwave background probes scales from about 1,000 or a gigaparsec, 1,000 megaparsecs, a gigaparsec or so, a few gigaparsecs, all the way to tens of megaparsecs. Now, all the stuff we see around us is here. Galaxies, clusters, superclusters. They're much smaller than the scales probed by the CMB. And so, really, if you want to test the theory, the CMB is not enough. You need to see how these fluctuations evolve to the present day. And so, I'm going to then now try to test these ideas on small scales using the galaxy distribution to tell us whether really the power spectrum that we see today is consistent with what we see at early times and what the theory predicts. It also turns out you can do a very direct test. The structure actually grew by gravitational instability. And if I have time, I say a little bit about how we can use the theory, use observation of galaxy formation to test the cosmological theory. So let me begin then with the most basic test you can do and ask the question, is the power spectrum of the galaxy distribution today consistent with the theoretical prediction? Need to know what the theoretical prediction is, of course, first of all. And so in order to know what to expect, you need to be able to simulate that. And I'm going to start by showing now a movie from the Millennium simulation that we've talked about so many times before. That's step one in trying to make theoretical predictions. And in this movie, in this simulation, as I said earlier, there are 10 billion particles distributed in a volume, cubical volume of side 500 megaparsecs, so that the simulation resolves about 20 million galaxies that would be brighter than the Large Magellanic Cloud. And as you would have inferred, these data have been made public. The simulation is now quite old, it's 3 years old, but the data were made publicly available very soon after they were obtained. Now, the simulation was carried out at a big supercomputer in Munich, the RZG. You see the supercomputer here. Now, I don't know how many of you have been inside a supercomputer room. You have these big machines there, this huge amount of noise, there's wind blowing everywhere. You walk in there and you say, well, where's the brain? What's actually doing the calculation? And in the case of this computer, we know exactly what the brains are. That's Simon White, and this is Volker Springel. You can see Simon smiling, Volker serious. You might wonder, what did Simon look like when he was the same age as Volker Springel? And that's what he looked like. And he was already smiling. It hasn't changed that much. But at any rate, so let me now show you a movie that illustrates the distribution of dark matter in the Millennium simulation. So this at redshift 0, we're just going to zoom into a particularly interesting object. And we start actually looking at a universe on much larger scales than the Millennium. This was a previous simulation we did with a very good consortium called the Hubble Volume simulation, which was much bigger. And we're going to zoom in a minute onto the Millennium, I hope. So here you see on these very large scales, the universe is very uniform. Here is the size of the Millennium simulation. And here you see the dark matter. This is all dark matter at redshift 0. The dark matter distribution at, I hope I didn't stop it. The dark matter distribution of very large scales. And I succeeded in stopping the movie. Hold on. This happened a few times here. I love my Mac, but not this one. Okay. I know there is a way to fix it. Oh my! Maybe we should have coffee. No, I'm just kidding. The trouble is, there we go. Good. Okay. All right. So let's start again. But you can see here the large-scale structure of the universe, very smooth and uniform, size of the Millennium. And now I say we're going to zoom into one of the richest clusters in the simulation. You see it in the middle, and here's the scale. So as we zoom in, you'll see increasing degrees of structure. And you can see here how the dark matter is distributed in this characteristic filamentary distribution that I've already mentioned earlier. At this sort of resolution here, you see how enlightened Dick Bond was when he coined the phrase the cosmic web. This looks like a cosmic web. You see these filaments that join together and surround regions of lower density. At the intersection of the big filaments, you see these large concentrations of mass. This has the mass of a galaxy cluster, like the Coma cluster. And you actually see that the filaments are broken up into halos. All these dark matter halos tend to be distributed along the filaments. And you see here the huge richness of structure that forms. Most of the halos are small, but there are also these large halos. And as we zoom into this galaxy cluster, you see how lots of substructure has survived in the outer parts of the halo. You see very nicely what Simon was talking about a few minutes ago. Here's the galaxy cluster. The central parts are quite smooth. All the substructures are actually in the outer parts. You see all these big, massive substructures tend to be far away from the center, which is quite smooth. This is not a galaxy. This is a galaxy cluster, and presumably these are all the cluster galaxies. You see very nicely here, although with much poorer resolution, what Simon was talking about earlier on. Now, Simon already showed the fly-through. I want to show it again because I think this is a great movie. It won several prizes, actually, on television in Germany and the United Kingdom. And it really tells you what CDM is all about, at least insofar as you had dark matter glasses. You could see then this amazing richness of structure. Galaxies, of course, would form in these objects as gas cools into them and then fragments into stars. And you see these very nice filaments here with the rich mass concentrations forming at the intersection, in this case, of 3 or 4 filaments. So that's what comes out of these Gaussian random fields with the power spectrum that I showed.
What are the colors?
The colors is just the density. It's a measure of density and velocity dispersion. So it's a combination of density and velocity such that it highlights regions of different, it allows you to distinguish regions of different density. It's just dark matter. Now, so let's now see how we analyze the simulation quantitatively. First thing you want to measure is the power spectrum. And here it is. The power spectrum, this is what I used to call k cubed times delta k squared in my last lecture. So that's the total power per decade in spatial frequency, large scales, small scales here. And here you see the power spectrum in blue at different epochs from redshift 15, redshift 7, 3, 1, and 0. Now here on large scales, the gray lines are the predictions of linear theory, the linear theory that I developed last time. You can use to calculate how the power spectrum should grow. If omega was 1, this would just grow in proportion to expansion factor. A bit more complicated with lambda, but that's what linear theory predicts. Now you see here on large scales, the simulations agree beautifully with linear theory, as they should do. These perturbations still have very small density contrast, very small amplitude. But here, on increasing on large scales, on small scales rather, as time goes by, you can see that the power spectrum deviates from linear theory. That is the effect of nonlinearity, the effect of fluctuations becoming overdense and collapsing. This, in the mathematical terms, arises from the coupling of the phases of these different waves that cause power to drain from large scales to smaller scales. Now here by redshift 0, you can see that the nonlinear amplification is very, very large, several orders of magnitude. Here on values of k of about 10 or so, a few megaparsecs, the nonlinear amplification is many orders of magnitude. But something that's quite interesting is that we begin to see deviations from nonlinearity at surprisingly large separations. This k of 0.1, 0.2 corresponds to scales of hundreds of megaparsecs, and even there already the effects of nonlinearity begin to be important. And as I will argue later, that's important when you want to interpret or measure dark energy from baryon acoustic oscillations, for example. Now, ideally, if you really wanted to test the theory, you like to measure in nature that power spectrum of the dark matter, and we can't yet, but we will perhaps in future, exploiting gravitational lensing. So there has been talked about before, there are many surveys that are trying to measure the power spectrum by looking at the shear induced by gravitational lensing. Here's the kind of things that will be possible. This very early data, this is the first time, it's already several years old, where something related to the power spectrum as a function of scale was measured. You can see there hasn't been much progress until very recently in this field. These fields move quite slowly. That's the reason I chose to show you a very old plot. If I show you the latest, well, the latest plot, the latest data has only just been released, but it doesn't look much better than this. Systematics are a bit more under control, but these are very slowly moving fields because the measurements are very complicated, and one is trying to look at signals that are really rather tiny. So I think there's a lot of future. We're supposed to be telling you about future directions of research in this field. I think gravitational lensing has enormous potential because the techniques are getting better, and it will provide eventually a very direct test of the cosmological paradigm. However, we're not there yet. At the moment, this is what we have. We have galaxies, and so if we now want to use galaxies to test the theory, unfortunately, we now need to understand something about galaxy formation. I say unfortunately because it's very complicated. On the other hand, it's also a very rich topic in its own right. And so he wants me to stop in 5 minutes. So I'm going to give you a 5-minute crash course on galaxy formation. That's all I'm going to do, 5 minutes on galaxy formation. Let me just point out there are 2 steps. One is understanding the evolution of dark matter, which we have under control through embodied simulations. And then you need to understand the gas processes, which are much more complicated. So where do you start? Well, if you want to make a galaxy, you need a dark matter halo. We know everything we want to know about dark matter halos from simulations. And in particular, we know the mass function of halos. If you want to know how many galaxies you have of different luminosities, first thing you need to know is how many halos you have of different mass. And that so-called halo mass function, number of halos, function of mass, we know perfectly well from simulations, given the cosmological model, Lambda CDM in this case. Now, if you are a small child and you're asked give me a galaxy formation, and you have blobs of different size, well, what will you do? So you have balls of different size, and you have your Rice Krispies, and you say, tell me how the Rice Krispies I should be distributed in the balls. If you're a small kid, you take an amount of Rice Krispies, small amount if the halo is small, big if the halo is big. So that would be a naive way of trying to populate halos with galaxies. And if you do that, sorry, we also know, let me skip. I was going to say we know not only how many halos there are, we also know what the structure looks like. So if you do that, you get completely the wrong answer. And that's illustrated here. This is the halo mass function that I just showed you, and this is the galaxy luminosity function. And you can see this observed. This from observations from Sloan and 2DF. That's what the galaxy luminosity function looks like, the number of galaxies, function of magnitude. And it has completely a different shape from the halo mass function. That means that Rice Krispies weren't put in equal amounts in proportion to the mass in each halo. Instead, there are complicated astrophysics going on. There's a complicated variation of the amount of light put as a function of mass in halos of different mass. And figuring out the transformation between this halo mass function and the galaxy luminosity function is called a theory of galaxy formation. So that's what the theory has. You need to take into account a large number of processes. You need to know how gas cools in halos, how it turns into stars. Now, stars tend to blow up and produce a radiation, and that, of course, feeds back into the gas that's trying to cool. That's called feedback. There are metals, there are stars that evolve, there's dust, there are black holes, and all these things are processes that we're beginning to understand in increasing detail. Now, however, even if you do a gas simulation, the best you can do really is resolve the formation of halos, as in the millennium, and you can also calculate with considerable accuracy how actually gas cools inside these halos. All these other astrophysical processes are not yet, it's not yet possible to simulate in ab initio. In a hydro simulation, you need to use what we call subgrid physics to solve them. Now, there are hydro simulations you can do, and I'm going to show you one by Takashi Okamoto, former postdoc at Durham. And here you see in the Lambda CDM universe how a galaxy would form. Here you see gas in two projections. Here you see stars. You can see gas before stars because gas has to collect and cool before stars form. Here you see the formation of stars. And you see what Simon was talking about yesterday. Only a few major mergers take place in the formation of a typical galaxy. As time goes by, you see that these galaxies form a very nice spiral disk, quite thin, with spiral arms, both in gas and stars. And so there's progress in this area, but this area is still at a very early stage. One can actually begin to make galaxies that look like real galaxies, but when you look at them in detail, there are still many things that don't work out. And so there's a lot of progress still to be made in this area. It's a very rich area, although technically quite complex. However, there's no chance of doing a calculation like that on the Millennium Volume. Forget it. There's no computer that we can even dream of that would allow you to do a calculation like the one I showed in every halo in the Millennium. And in fact, computing time you need to do that one galaxy is comparable to the computer resources you need to do the whole Millennium in dark matter. And so what I'm going to tell you about tomorrow is how you try to compensate for that and how you actually populate a simulation like this with galaxies, not using direct hydro simulation, but using physics, going back to basic physics and writing down scaling laws that allow you to put galaxies in here so that you can then go and compare directly with the observations, for example, of Sloan or 2DF. And I'll stop here.